Good afternoon. Welcome to join the AFOMP second webinar, monthly webinar. So today, we will have Dr. Aaron Jacques to give us a talk on the biological, and our monitor today is Dr. Chai Hong Yong. She's a medical physics certificated radiation protection officer and associate professor at the Taylor's University, Malaysia. And she's very active in the research and the clinicals. I saw lots of his titles. Currently, she's chairing the professional relation committee of the AFOMP and also a work subcommittee of the International Organization of Medical Physics. She's also the elected vice president of the Southeast Asian Federation of the Organization for Medical Physics and the founding member of the Asian College of Medical Physics. She has many research interests, so she has been published extensively in academic journals and preceding academic books and book chapters. Now I would like to hand the microphone to Dr. Chai Hong Yong. So she will moderate the talk today. So Dr. Chai.
Thank you very much, Jin, for the introduction. Good morning, good afternoon, and good evening to everyone. Welcome to the second AFOMP monthly webinar for July 2020. It's exciting to see the active participations of medical physicists in the region and also from around the world. We currently have 109 participants. I'm pleased to announce that the AFOMP monthly webinar is endorsed by the Australasian College of Physical Scientists and Engineers in Medicine. All participants registered and attended the full webinar today are entitled for CPT points of 2 credits. Please kindly register yourself using the link posted in the chat room, and e-certificate will be emailed to you in about 1 or 2 days after the webinar. Without further ado, let me introduce our speakers today. It's my great honor to introduce Professor Dr. Arun Choudhury, who is the current president of AFOMP. Dr. Arun Choudhury is the senior professor and head of departments of radiological physics, SMS Medical College and Hospitals, Jaipur. He is the former pro-vice chancellor of Rajasthan University of Health Sciences and the current dean faculty of paramedical science, Jaipur. Sorry, can I just check whether you are seeing my slides?
Yeah.
Okay, good. So Professor Arun has 30 years of professional and teaching experience in medical physics. He's one of the pioneers in radiation biology and experiment dosimetry in India. Professor Arun is the past president of Association of Medical Physicists of India, AMPI, and currently the president of AFOMP, as well as the chair of Education and Training Committee of IOMP. He has served as an expert to IEA and has been regular associate to ICTP for 8 years. He has been awarded with numerous fellowships and awards, mainly the IOMP IDMP 2016 Awards, AFOMP Member Excellent Presentation Awards, Outstanding Faculty Award 2019, and Dr. Farouz Abdullah Sher E. Kashmir Best Researcher Awards for 2011 and 12. So the topic of his presentation today is the radiobiology of radiotherapy, nominal standard dose to biologically effective dose. This is an essential topic, not only for medical physicists, but also for our clinical and allied health colleagues who are working in the field of radiotherapy or radiation therapy. Before I invite Professor Dr. Arun Choudhury, I'd like to kindly ask your cooperation to stop your video and mute your mic to save the bandwidth. You are very much encouraged to post your questions in the chat room during the sessions. Ladies and gentlemen, let's welcome Professor Dr. Arun Choudhury. Prof, the floor is yours.
Thank you very much, Chai Hong, for your kind introduction. And I take this opportunity to welcome all the participants of this AFOMP second webinar. And as the moderator has told you, that this webinar has been CPD accredited and 2 points you will get it. And that's what you have to send the email. So today's topic is radiobiology of radiotherapy, NSD to BED, that is a nominal standard dose to biologically effective dose. And radiobiology is applicable not only to radiotherapy, radiation protection, clinical aspects and all. So the presentation of my today's will be divided into three parts. The first part I will talk about the basic radiobiology. In second part, I will put the scope to the radiobiology applied to the radiotherapy and fractionation in radiotherapy. And in third part, I will talk about the radiobiological models. Now, what is radiobiology? As you know very well, that radiobiology is a branch of science which combines the basic principle of physics and biology and is concerned with the action of ionizing radiation on biological tissues and living organism. It entails the physics, chemistry, and biology, all the three. As you very well know, little historical background, within 10 years of discovery of X-rays and radioactivity, which was put immediately for the radiotherapy and radiodiagnosis, Bergoni and Tribundo in 1906 irradiated the scrotum of the ship, and they found that the cells which are multiplying, which are rapidly dividing, which are undifferentiated, they are highly radiosensitive. And this gives the first biological differential action of radiation evidence in way back in 1906, we call B and T law or Bergoni and Tribundo law. And according to these things, cell response to the ionizing radiation is highly radiosensitive, moderate radiosensitive, and radioresistant. Lymphocytes, spermatogonia, which are fastly dividing, highly dividing, undifferentiated, they are highly radiosensitive. Osteoblasts, spermatids, muscle cells, which are moderately radiosensitive, and nerve cells, which are completely divided, they are radioresistant. When the radiation interacts with matter, in our case, it is a human body or any organism, animal cell, X-ray, they give rise to secondary electron. Secondary electron gives rise to the free radical. These free radical takes into chemical change, chemical reaction, very highly active, and they lead to biological effect. So physical transfer of energy, chemical changes, and that chemical changes lead to a biological effect. You must understand the physical, biological, chemical, and biological properties of the ionizing radiation. We can classify the ionizing radiation effect on a living cell as one is an indirect route, wherein the ionizing radiation interacts with the water into the tissue and gives rise to free radicals. And these free radicals are very highly chemically reactive, and in turn they will damage the chromosome, they will break the double strand break, single strand break, and lead to sublethal or lethal damage. This is called as an indirect route, wherein formation of free radicals are taking place, and because the free radical formation is happening, chemical reaction, this can be accelerated or decelerated by using radiosensitizers or radioprotector. And second is a direct route, wherein the radiation directly hits the chromosome and the damage takes place. It can be sublethal or lethal damage, that is called as a direct route. Generally, X and gamma radiation or photon leads maximum effect is indirect route, for free radical formation, and the particle radiation, they go through the direct route. And then when the radiation interacts with the cell, two major possibilities are possible. One is a lethal and sublethal. Lethal means cell will end up, it will die, cell will not exist or survive. Sublethal damage means cell is damaged but survives. Now, if the cell repair, complete repair takes place and it functions as a normal tissue, there is a one cell survives, but the damage persists and there can be mutation and it survives as a atypical cell. Now we'll see very important quantities or parameters into radiobiology, which determines the radiobiological effectiveness, and that is called as LET, linear energy transferred. Second is RBE, radiobiological effectiveness, and third is oxygen enhancement ratio. One by one, we'll try to see it. LET is a linear energy transfer. When the radiation enters into the matter, in our case, a human body or a tissue, it deposits the energy. As you know, alpha particle, most of the energy is deposited into short distance, and therefore they have high LET radiation. KeV per micron is very high. X-rays and photon, they go on depositing the energy, and therefore they are called as low LET radiation. So low LET radiation, gamma rays or X-rays, and high LET radiations are alpha particle, ions of heavy nuclei, charged particle, low energy neutron. They are high LET radiation, and they deposit a lot of energy into a short distance. Now, the third quantity, second quantity we'll see, that is called as the RBE, relative biological effectiveness of different kind of radiation with a different kind of tissues in terms of different effects. So these are relative capabilities of a radiation with the differing LETs to produce particular biological response. This is called as the RBE. And if we want to define it RB into absolute term, dose required in gray from 250 kVp X-rays divided by dose in gray of the test radiation to produce a particular biological effect, that is called as RBE. And here you can see RBE, we have a particulate radiation and we have X-rays, and this is the cell killing. So for 10% survival, that is a 90% killing, dose required by the particular radiation as compared to X-rays is much, much lesser than the X-rays. So this dose divided by this dose will give me the RBE of the particulate radiation. Now, what is the relation between the linear energy transfer and RBE? You see it from the graph. As LET increases from keV micron to MeV micron, you can see that for X and gamma radiation, the RBE is almost 1. But as the linear energy transfer increases, that is for the particulate radiation, the RBE increases, it can go up to 7 or 8 also. So LET increases, radiobiological effectiveness will increase. Now we'll see the third quantity, that is oxygen enhancement ratio, OER. The ratio of the radiation dose required to cause a particular biological response on the cells or organism in an oxygen deprived anoxic environment to the radiation dose required to cause an identical response under normal oxygenated conditions. And therefore, OER is actually related with the indirect effect because oxygen is one of the sensitizer. If there is an oxygen present, the free radical formation will be accelerated or enhanced, and it will end into higher biological effect. So if you look at LET and OER, the low LET radiation, which is X and gamma radiation, OER effect is almost of the order of 3. What do I mean by this thing? I mean by this thing, in the presence of oxygen, 3 times more cell will be killed than in absence of the oxygen for a particular effect or particular amount of dose. So as the LET increases, the OER effect comes down to 1, and therefore the particulate radiation, which the effect is not dependent on the presence of oxygen, and therefore this is utilized into a particulate radiation particle therapy, that is the proton therapy or carbon or different ion therapy, because the tumors which are very solid where oxygen is supply is less, or chordosarcomas where the blood supply oxygen supply is less, which are resistant to X or gamma radiation, will be sensitive with this high LET radiation, particulate radiation. So LET increases, OER decreases. And just one example of different kind of radiation, if you see it, the gamma rays, we have OER almost of the order of 3, but the RBE is 1. As we come down to protons, helium, negative or fast neutron, you see that the OER comes down and RBE increases, the biological effectivity will increase and dependence on the oxygen will decrease. Now another example with the X-ray, just I said, and to the particle therapy. Here if you see the cells which are hypoxic and cells which are oxygenated, to get a particular cell killing or cell survival, you can see it here, the hypoxic cell will require much higher dose than the well oxygenated in case of X-rays or photons, and therefore OER is of 2.5 to 3. But when we move to the particulate radiation, this gap between the well oxygenated and hypoxic cell decreases and almost it vanishes between the alpha particles or this thing, so OER ratio is just 1. Now, in 125 years of radiotherapy was started just within few months of the discovery of the X-rays, way back in March 1896. Emil Grube treated the first cancer patient, it is said, and then lot of development has taken place into the clinical advancement have taken, technological and biological. This in blue, biological. This depicts 1906, that is a Burgonian Tribundu cellular radiosensitivity depends upon the mitotic activity. Then we understood during 1920s radiosensitivity correlated with the oxygen presence, and further go on. During the 1980s, we found out tumor potential doubling time and how it affects the tumor control probability. Isotopic formula that LQ models were given. So radiobiology, along with the physical and technological things, is progressing. Understanding of the underneath biology has been understood very well now, and we are using that thing. Now I come down to part 2, radiobiology of radiotherapy and fractionation. How can we use effectively the fractionation schedule, dose per fraction, to get a better tumor control probability and keeping the normal tissue complexion probability at a manageable thing. Our primary aim of radiotherapy is to deliver a lethal dose to the tumor. We want to kill all the cancer cells in the tumor, but at the same time, we want to spare the normal tissue and organ at risk, or we want to keep the comorbidity, normal tissue comorbidity, at a manageable level. How to do it? It's an art and it's a science. If you look at the radiation dose and the incidence of the effect, that is the sublethal or lethal damage, what is going to happen, you will find that tumor control, the line is a sigmoid one, and also the normal tissue damage is a sigmoid one, but the tumor control, the line is towards the left of the normal tissue, then only radiotherapy will be successful. And here you can see a simple example by example. At this dose, I get the normal tissue damage is around maybe 10%. But at the same time, this dose gives me about 60% of the tumor control probability. Control this thing. With now different fractionation schedules and techniques we have got, we can widen our this gap between tumor control and normal tissue, and we can escalate the dose, keeping the normal tissue damage at a manageable. Here you can see for a given fractionation schedule, this is a tumor control probability, and if you have a large volume and we are treating with a 3D CRT where volume is large, normal tissue radiation also is there. You see here that for this dose of about maybe 75 gray, I am going to get almost about 45% the complication probability normal tissue to get about the 85% of the tumor control probability. But you can see it here, if the volume is very small, tight margins we have taken, confined IMRT, and with proton, you can see for the same tumor control probability, my normal tissue complication rate will be hardly 5 or 10%. And that is how we can escalate the dose and try to achieve the tumor control probability. So 4 hours of dose fractionation, you know very well. Just I will name this thing: repair of the sublethal damage. The lethal damage cannot be repaired, only the sublethal damage will be repaired. Redistribution of the cell during the cell cycle takes place. As you know, the synthetic phase, in mitotic phase, and in the growth phase, they are there. Redistribution takes place, repopulation of the cells takes place, and the reoxygenation during the fractionation time in between the repopulation and reoxygen take place. These are called as the 4 hours of the radiotherapy. And 4 hours of the radiotherapy, we look at this thing. Within just hours, the repair process starts, redistribution within few hours, and reoxygenation. But repopulation is one delayed one. And we have to see that we do not extend our treatment so that the repopulation of the cancer cells also get triggered. So we have to plan the 4 hours of radiotherapy, influence and time between the fraction T, overall treatment time T. So reoxygenation, repair, and repopulation must be used so that we get a better tumor control probability and the normal tissue compression will be less. But they cannot achieve all at once. Optimizing the schedule for individual circumstances, a tailor-made treatment is needed. Now we have also understood that radiosensitivity, it's an in-peak radiosensitivity, is a very, very important for the tumor control probability, or achieving our end point is achieving a better tumor control probability, keeping the normal tissue composition probability within the acceptable, manageable. So fifth is a very, very important. And when you plan the radiation oncology, the fractionation schedule, dose, team, fraction size, volume, the larger the volume, larger the reactions, and the morbidity will be there. So interdependent, and then you can use sensitizers to sensitize the action on the cancer cell. You can use the protectors to protect the normal tissues, and you plan radiotherapy. So time, dose, and fractionation need to optimize fractionation schedule for individual circumstances. And the parameters in your hand to do this are the total dose, what you are going to give, what the dose fractionation you are going to get, what is the time gap between the fractions, and the total treatment time, what you are going to do. So you have these 4 parameters, and you cleverly play with this parameter address and then plan a schedule which gives you very good outcome in terms of tumor control probability. The most important things the history has taught us are there can be no single regimen for treatment delivery that will be appropriate for all tumors in all patients. So there will be various types of protocols, regimes, fractionation schedule for different kind of tumor, different kind of sites. So fractionation cannot be considered in isolation. There is a complex interdependence between the total dose, dose per fraction, overall treatment time, treated volume, and the beam parameter. And our job is to optimize this thing. Then fractionation schedules here, just to look at, there are conventional fractionation schedule where we use 1.8 to 2 gray, almost about 9 to 10 gray per week, and about 40 to 70 gray into 30 to 35 fractions. Hyperfractionation is time, total treatment time remains the same of the conventional fractionation, but you have a smaller fractions than this 1.8, and therefore you have to use 2 or 3 fractions in a day, and gap between the fractions should be minimum 6 hours. Less than that, you will end up with this. Then third is accelerated fractionation, where overall treatment time is shortened, more dose is delivered per week, and hypofractionation, where dose per fraction is higher than 2.2 gray, reduce total number of fraction to get the same biological effectiveness, and hence treatment time also is reduced. So hypofractionation, then you can see it here, conventional and hyperfractionation, the total treatment time remains the same, but the number of fractionation in hyperfractionation increases, and we go for 2 or 3 fractions per day, making the little higher dose. With the accelerated fractionation, the time is reduced, and the reduced time we give the equivalent dose as per the conventional this thing. So now types of hypofractionation. Hypofractionation has been further subdivided into 2 types. One is a moderate hypofractionation, wherein my fractionation doses are 2.4 to 4 gray, and 15 to 30 fractions are given to a total dose of 60 or to 70 gray. Extreme hypofractionation, where the dose per fraction has been increased from 6.5 to 10 gray per fraction, and the number of fractions are reduced to 4 to 7. This is called as extreme hypofractionation. Now you look at the radiobiology of the cancer is a very complex, and number of times in a clinic we come across the situation where tumor size is very large. It's a T4 lesion, but that regresses completely, and the T2 lesion, which was smaller the size, end up into residual or recurrence. So it is not the tumor size, but the chronological cells or the stem cells, the doubling time, apoptic tendency, so many biological heterogeneity in the tumor is there, which needs to be considered. And here you'll see number of chronologic stem cells which are omnipotent. They divide, they get differentiated. Intrinsic radiosensitivity we have seen. Proliferative potential, that is develop the multiplication potential. Pro-apoptic tendency, that is the cells go into suicidal. Beyond the cell death is called as a pro-apoptic tendency. Repair, T-half, fast or slow. Rate of repopulation, regeneration, T-potent doubling time, the growth fraction, hypoxia, metabolism, host cell infiltrate, oncogene, tumor suppressor gene. These are some of the biological heterogeneous within the tumor, and the physical heterogeneity is the dose heterogeneity, uneven dose distribution, hotspot or cold spot, or a geometrical miss in the IMRT or other type of modality. Just one example of the stem cells, I will show it here. The renewing stem cell, this is a stem cell, this divides and then go ahead and dividing and dividing. These are non-stem cell, they will not further go on dividing. But if you have a tumor here, and after radiation, if you end up into killing most of the stem cell, your tumor cure possibility will increase. But you end up in a stem cell, there will be residual stem cell. After some time, again they will multiply and grow. This will lead to the failure of the tumor. So it's not just size of the tumor, but the underneath biology, the chronological cell number. Another example, just I will give it here. You can see chronological cell number 10⁻⁹ or 10⁻⁸ or 10⁻11. Just this example I will take. I give a 70 gray dose. If the chronological cell number is 10⁻11 in the tumor, I may expect only hardly 10% of tumor control probability. With a 70 gray in a tumor which has 10⁻10 chronological cells, my tumor control probability will shoot to almost 80%. And if the cell chronological number is 10⁻9 or less, almost about 90% tumor control probability I will achieve. So very important factor in radiotherapy, radiobiology is the chronological numbers of that's the stem cell. Another example of a tumor kinetics, how the fast dividing, fast growing tumors and slow growing tumor we classify. And when I come to radiobiology, the alpha by beta ratios depends upon this thing. An example of human squamous cell carcinoma, if you take it, a cell cycle time is 36 hours. And in this cell cycle, the growth fraction added is 0.25 or 1.4. So to make double the number of cells after a certain time, we need 36 hours into 4 divisions. You have to take it 36 into 4, 6 days will be required. But actual doubling time is 60 days because your apoptosis is happening, radiation cell killing is happening during the treatment, and therefore ultimately the cell loss factor is 0.9, very high. But if the actual doubling time is less, it may be 20 days or 10 days, my cell loss fraction will be 0.5 or 0.4. So despite of radiation, the cancer cell death will be less than 30 or 40% cells are getting regenerated. So the cell kinetics is a very, very important. Another example of oxygenation, which is a radiosensitizer. You can see a tumor. Generally on the surface, the tumor cells are oxic because of the blood supply. When you give the radiation on the first day, this aerated, the cells will get irradiated, and the lethal dose because of the OER effect, tumor gets sink. After a gap of about 24 hours, the cells which were anoxic, mostly hypoxic, they get oxygenated. Again, another fraction is given. The cells becomes OER effect will happen. The lethal dose goes on. With a fractionation, we can bring down. So oxygen plays a very, very big role in a photon treatment, X-rays or gamma ray, where OER is a very, very important. Hypoxia and local control, tumor control, if you look at this example, you look at the small hypoxic cell number and large hypoxic cell fractions were available in this. So 24-month local control probability, if you see where the median oxygen supply or hypoxic cell fraction was much higher, I can just expect only 40% tumor control, and here it's almost more than 80. But if I see even 5 years disease-free survival also, you'll see that if the oxygen PO2, and that can be measured also, it's more than 10 millimeter of Hg, and this is less than 10 millimeter, you can see almost double the tumor control or disease-free survival you can achieve. So oxygen plays a big role. Also, the microvascular density in the tumor leads to metastasization failure of the tumor. Here you can see the microvascular density is much less, so possibility of metastasization is less. As the microvascularity increases, and then the metastasization probability increases, and that is what I will not discuss here much, but flash therapy radiobiology is here. As I told you, since the radiotherapy, we have progressed a lot, and confirmation, CI, the confirmation index, or the confining the dose to the tumor, the technology, the kind of radiation, the planning system, and here you can see this is the dose bath. The large area, normal tissue has been receiving very large dose. But as you move on, you can see we can confine our dose to the tumor, and therefore we can escalate the dose and attain very high tumor control probability, and very small normal tissue or the organ has been completely out of this dose, isodose curve, and therefore we can spare this thing and achieve. So now I will move on to the third part of my talk, and I hope you are able to listen me. My voice is all right. Is it okay? Are you? Everything is audible?
Yes, it's very good, Prof. Arun.
Okay, that's good.
Okay. Then so we'll go to radiobiological model. Now, first question comes to mind: why do we need radiological model at the first place itself? Because just we have seen that all the tumors are not treated with the same time dose fractionation schedule. because repair, repopulation, redensity, and all these 5 R's plays a big role, and therefore we have to have different fractionation schedules. All the radiation oncologists in the institution or other institution will not treat similar tumors with the schedules followed by others. Many fractionation schedules encounter gaps. They may be planned or unplanned. Planned means I have planned a 30 fractions of the treatment, and after some reaction I want to stop it and then give a gap of 1 month and then again treat it, fine. But for example, in COVID, we have started a treatment, and because of the COVID, the hospital was not able to function, or some other problem, or patient could not come. There's a gap. Now, after some gap, maybe a 1 month or 2 month patient comes, how many fractions should be added to get the same biological effect? That we must understand, we must do. Combination of brachytherapy. We treat cancer cervix or many other patients, cancers with external beam radiotherapy and brachytherapy. And we want to look at a combined effect radiobiologically, not just adding a physical dose. We have brachytherapy, HDR and LDR. Then also just I talked about hypo, extreme fractionation, the fractionation schedule. So many fractionation schedules are there. Since the treatment schedules are numerous and different from each other, it is rather difficult to intercompare them unless they can be reduced to preferably a single number which indicates me the tumor control probability or radiobiological effectiveness or normal tissue damage. How many parameters are needed and how important are the exact numerical values, that we will study, and I will just try to put forth you. Radiobiological effectiveness of various dose fractionation schedules on normal and tumor are different. Early effect, late effects are different, and therefore we need radiobiological models which can be used to compare the outcome of different fractionation schedules you are practicing, or you want to move from one fractionation schedule to another fractionation schedule, or you encounter the gaps, or you have a brachy plus external beam therapy, how to merge and get the biological end result that is there. So various concepts of time dose fractionations were introduced in 1950s to correlate the biological effectiveness. Now, biological modeling, what you have to do, you have to get a mathematical expression, and you have to do the mathematical manipulation to incorporate the components of radiobiology. And then this radiobiological model which is there, you have to correlate with a clinical outcome, and then accordingly you can modify, add scaling factor, and this modified model to fit the clinical outcome, how this biological models are devised, proposed, and there are many kind of biological models. Just I will discuss with you. Stankis was the first in 1944. He gave a scientific approach, and he related the dose given and in a time in which it is given to get a particular biological effect. And this he plotted a log time and log dose to get effect on the tumor and effect on the skin, and he ended up into these lines. Cohen, 1949, analyzed the data of Reisner, Quimby, and Stanquist, and he showed that the dose is directly proportional to time over which is given raised to n to get a particular biological effect. And then he equated D is equal to K T raised to n. This is just little mathematical jugglery. I will not go into much more details of that thing. D is the total dose and T is the time. And then two lines we have seen, the slopes are, one is 0.33 for the normal tissue, 0.22 for the malignant tissue, and they put this into this formula, same d k t raised to n power. Power is 0.33 and 0.22, and that gives the intracellular alkyne kind of recovery, which is represented by the t raised to 0.22, and homeostatic recovery represented by t raised to 0.11. Further mathematical jugglery was done by the Ellis in 1969, and what he did, we know the standard protocol, standard treatment which was going on, 30 fraction, 5 fraction week, 60 gray in 6 weeks, that is 40 days or 42 days. What he did, he tried to relate the time and the number of fraction. We know the time is 40 days or 42 days. 6 weeks it can be 40 or 42 days. And the number of fraction n, so the power game it had changed. And then therefore the normal tissue, he is going to replace the t with n now. Yeah, n. And this is how it is come. And then Ellis termed the constant k as NSD, nominal standard dose NSD. So what you should remember and look at the formula is that the nominal standard dose, first biological, model, empirical, power relation, dose, total dose, n number of fraction, and t, this t is the time divided by the number of fraction, this is power. So this NSD was given, and as you know, D is 60 gray, N is 30, and T is 7/5, that is a 7 days, 5 fraction we give. We end up in, for a standard treatment, NSD, that is 30 fractions of 2 gray to 60 gray, 1800 rates, and this rates unit of radiation equivalent therapy. So first biological model, empirical model by Ellis gives me NSD. Now, another concept was introduced, that is a cumulative radiation effect, because NSD was not useful for the sub-tolerance dose. It was only the endpoint total dose, number of fractions. And therefore, Kirk in 1971 gave CRE formula, cumulative radiation effect, and here you can see dose per fraction, n number of fraction, and x is the days divided by number of fraction. This is valid for any number of fraction, any number of the fractional dose, it is valid, and therefore for sub-tolerance also it is valid, and the unit is REU, radiation effect. Also, Kirk gave us for the CRE for brachytherapy. In earlier days, it was a continuous brachytherapy, either the LDR or MDR, and then he gave 0.53, the scaling factor, 0.53, so just I told you that you have to see and then scale it so that it coincides, or you have a correlation between the clinical outcome and the prediction of the mathematical model. R is the dose rate, centigrade per hour, and T is the treatment time in hours, because that was the LDR and MDR treatment. Concept of time dose fractionation was given by Orton and Ellis in 1973, and they developed time dose fractionation, very, very widely used. Still people use this thing, and TDF is given as dose D raised to 0.538, and the number of fraction X, just I told you 7/5 is 1.4 raised to this, and this is a scaling factor to make this number useful. And for continuous therapy, that is a brachytherapy, they give this formula. They also give the gap correction. I told you that patient, you plan for 30 fraction, but for some or other reason, he takes 18 fraction and then vanishes and comes after 3 months. So is it just 12 fraction remaining should we give, or we have to add on the fraction to get the same biological effect what we planned earlier? So TDF is additive. For standard treatment, TDF is almost 100. That is a scaling factor which we use, -3 gives us 100. Table of 1 to 6 fraction per week were available. They were very easy to use, and they were used. And one table, just I will show it here. This is for the 5 fraction per week. How to use it? Very simple. So you have a 200 rats that time for 200 centigrade or 2 gray per fraction. If I give a 30 fraction, I end up in a TDF of 99. Now, for example, I want to shift, I don't want to give the 30 fraction. I want to give 300 per fraction. So to get the same biological effect, how many fractions I need to give so that I get the same? So 99 to achieve, about 19. So 16 fraction of 300 centigrade, that's a 40th gray, is equivalent to 2 gray per fraction, 5 fractions per week, 30 gray. Tables are very simple, very easy. They are available in literature. And the tables for the gap corrections also were given. So for example, patient take a treatment for 20 days and comes after, for example, after around 3 months. So this is a decay factor you have to apply for the TDF which he or she has received, and then add up and do that thing. So this gives me. So now just I will talk about, because I have to talk about the LQ model also, its applicability to hypofractionation and other fractionation schedules, also to the particle therapy. So limitations of NSD, CRE and TSD, TDF concepts were that these biological models do not take into account the complex biological process. They were just dependent on dose per fraction, number of fraction, and the treatment time, and the power equations. Only early effects they consider. They did not consider about the late effects. They did not consider about the tumor effect, and therefore the radiosensitivity, which depends upon many intrinsic factors, cell phase, mitotic rate, blood oxygen into nutrient supply tissue. So they lacked to get exact simulation of a biological process, and therefore a linear quadratic model, which the buzzword you are using, almost about 20-25 years we are using this for variety of radiotherapy schedules. The LQ model was originally proposed by Kellerer and Rossi in 1972. However, Berenson in 1982 applied it to a radiotherapy data, and he showed that the effect, that is the cell killing or the lethal or sublethal damage, E is equal to alpha D, D is the dose given, plus beta D square. This first term alpha D is a linear term, beta D square is a quadratic term, and therefore called as a linear quadratic model, linear plus quadratic. The first term is the effect linearly proportional to the dose, and this is a direct hit effect, single hit, and this is a multiple indirect hit effect. Individual alpha by beta values are not required, but we must know alpha by beta ratio for a particular effect, late or early, in a different kind of tissues. And therefore Berenson has done little manipulation into this thing. E divided by alpha, he did it. So E has, alpha has gone here. This equation becomes D, the total dose, 1 plus D alpha over beta. And this term into the bracket RE, that's a 1 plus D alpha over beta. And this term is D, the total dose is equal to, given into fractionation, number of fraction N and D. This E over alpha, the term is called as an extrapolated tolerance dose, ETD, or extrapolated response dose, ERD, or biological effective dose, BED. So BED is defined as number of fraction N, dose per fraction, 1 plus D over alpha by beta, which is a tissue specific, reaction specific, early or late. And here, therefore, ERD, BED, ETD is equal to this equation. Generally, for acute epithelial tissues, reactions in radiotherapy, normal tissue reactions, alpha by beta ranges between 8 to 13, maybe mucosal reactions, skin reaction, or a bladder reaction, early reaction I'm talking about, and average you can take it 12, published by Fowler 1984. Late tissues reaction, that is radiation myelitis, fibrosis, alpha by beta is in the range of 2 to 6. Tumor tends to be characterized by high alpha by beta, typically 10 to 25 for fastly growing tumor. But for the slow growing tumor, for example, prostate is a very slow growing tumor, alpha by beta is taken of the order of 1.5 to 2 gray. And for breast, which is a moderately proliferating tumor, it's taken as 5. Now, just you can see cell survival curve. If you see the cell survival curve, this is a linear portion which is represented by alpha D. That is, E is the effect is directly proportional to D alpha. And then this portion, which is a quadratic, is proportional to D square. So this is a single hit, and this is a multiple target, multiple hit effect can happen. Now here you can see that alpha component, linear variation with dose, unit is per gray, lethal damage, double strand break, predominant for the high LET radiation. Beta component is a quadratic variation with the dose per gray square. Damage can be repaired and is a single strand break. Now, what is this alpha by beta ratio? Where alpha by beta ratio is the dose at which the linear component, this component, and this quadratic component equals alpha D and beta D gets equal. That dose is called as alpha by beta. So alpha by beta has a unit of gray, that is actually a dose. So alpha by beta ratio defines the bending of the survival curve. Alpha by beta ratio is high, lethal damage is more because alpha component is higher than the beta. Curve linear at origin. Alpha by beta ratio is low, means alpha is less, beta is little higher. So that means damage can be repaired. Curve with a shoulder at the beginning. How to, yes, in literature, alpha by beta values are available, but you at your clinic, specific for your circumstances, you can estimate for your institute. How you can do that thing? You can plan various fractionation schedules, and you find out the iso effect dose with the various fractionation schedules to get a particular biological endpoint. Once you get the iso effect dose to get a biological effect, then you plot a FE plot, and that FE plot is 1 upon D, that is the iso effect dose which is there, to the dose required to get that biological effect versus dose per fraction. The slope will give you the alpha by beta. Another method is a Bohr's method. Same technique, you have to find out the iso effect doses at least 3 different fractionation schedules, and then you have to plot D versus DD plot, and you get alpha by beta. Tucker's method is there. By plot again you get alpha beta. So there are 3 methods available in literature, and we have published one paper in Physics Medical Biology in 1930, that is estimation of alpha by beta for early skin, late reactions and other things. And now, as I told you, the alpha by beta for human normal tissue variety, erythema, desquamation, mucositis, layering, local cord, everything is available. But generally for late reaction, you can take from 2 to 4 is alpha by beta. Early effect is around 10. Tumors can be, it's a fast growing about 8 or more than that. Slow growing, as just I talked about, prostate 1.5 to 2, and for the breast it's around 5. Now, what is the radiobiological basis of fractionation based on alpha by beta? How it defines, how it can direct us, or I can guide us to plan a fractionation. Large dose per fraction, that's a hypofractionation, more toxic to tissue with low alpha by beta ratio compared to tissue with high alpha by beta ratio. Now, if I take an example of prostate, I assume that it is alpha by beta is 1.8. Normal tissue, alpha by beta is around 10. So alpha by beta for normal tissue is 10. For tumor, it is 1.8. There's a vast difference. And therefore, this hypofraction will be more toxic on a tissue with low alpha by beta than the higher alpha beta normal tissue. So I will end up in a much more damage into this slow growing tumor than normal tissue. But if the alpha by beta ratio compared to the tissue with a high alpha by beta ratio, the hypofraction doesn't work if your tumor has the alpha by beta ratio 10, you have 8 or 9 is the alpha by beta ratio for mucositis or skin reactions or other reaction, then hypofractionation will end up into more tumor, less tumor control probability and more normal tissue, and there hyperfractionation is required. Another example I will tell you here, fractionation and the cell survival. Now, 2 gray into 6 fraction, 4 gray into 3 fraction, 6 gray into 2 fraction. That means I'm going 12 gray. Physical dose is the same. I given 2 gray per fraction or 4 gray or 6 gray, my physical dose is 12 gray. But biologically, all these 3 fractionations will not be the same. Just one example, 2 gray, 6 fractions I give. So this is example, this is a 2 gray, 2 gray, 2 gray. I give, sorry, this is a 2 gray, 2 gray, 2 gray, 6 fractions I give it here. I end up with the iso effect, the damage here this much. To get the same damage with a single fraction, you can see it here 2 to 4 and this is a 6. So it's a 4.8 gray. So biologically, 2 gray into 6 fraction, that is a 12 gray, is equivalent to 4.8 gray single fraction. Another example, if I give 4 gray into 3 fraction, this is 4 gray, 3 fractions I have given it. To get the same biological effect, a single fraction of 6 gray will be equivalent. So that way, if you have got a survival curve, you can get the radiobiologically equivalent fractionation schedules. Now, fractional sensitivity in different tumors in a clinical setting, if you look at, if alpha by beta ratio of a tumor, is higher than that of the late responding healthy tissue, head and neck cancers, if you take it, the tumor alpha by beta is of the order of 8 or 10. And late responding tissue alpha by beta is 3 or 4. And therefore, tumor alpha by beta is much higher. Here, your more smaller size fraction with a higher total dose will give you better tumor control probability and normal tissue probability within acceptable. Example, head and neck and lung cancer. Moderate to high, where alpha by beta ratio of a tumor is similar to or higher than that of the responding normal tissue. For example, breast alpha by beta is 5 and closely to the late effect of 3 or 4. Here, fewer larger size fraction might achieve same local control, example of a breast cancer. Now, if alpha by beta ratio is lesser than the late responding tissues, for example, prostate 1.5, 1.8 or 2, if I take it, alpha by beta of the tumor is lesser than that, fewer larger size fraction improve lower control. So how alpha by beta of a tumor and corresponding normal tissue early or late reaction guide you to make your fractionation schedule. Again, if you are going to from one fractionation schedule to another fractionation schedule, this BED helps you. For example, for a standard treatment, 2 gray per fraction, 5 fractions per week to total dose of 60 gray. Now, what will be BED for this thing? We have seen the relation BED is equal to N into D. Say N is number of fraction 30, D dose per fraction is 2. This D dose per fraction alpha, I have taken 10 for the tumor, and therefore BED for tumor with this fractionation schedule conventional, I get 72 gray. But BED for late reaction also I should calculate. And if I take late reaction, what I'm doing, same number of fractions, same dose per fraction, but alpha by beta value is changing from 10 to 2.5 because of a late reaction. And therefore my BED will be 108. Now, for example, I want to move or I want to find out a fractionation schedule with 3 gray per fraction, 5 fractions per week. What should be the total dose and how many fractions I need to give to achieve the same biological effect? For a standard treatment, for late effect, our BED was 108. To get this same BED, should not exceed the late effect. Now, my dose per fraction is 3. Number of fraction I don't know, I will do. And the alpha by beta is 2.5. So how many fractions I need? 16.36, that is equivalent to 16 fraction. It is 3 gray. So 3 gray, 16 fraction, 48 gray is equivalent to 2 gray per fraction to 60 gray. Now another example, a single fraction you want to give a large. 10 gray single fraction. How much is equivalent to your 2 gray per fraction? If you see it here, BED late, if I calculate 1 fraction of 10 gray, alpha by beta 2.5 are taken, 10 gray is a per fraction dose, I end up with the BED of 50. To get the same BED with the 2 gray per fraction, I need almost about 13.88, that's a 14 fraction, so 28 gray. So 28 gray given in 2 fraction per day is equivalent to 10 gray single fraction biologically. That is what the calculation of BED helps. I will not go into details of this thing. So you can prepare, and we have prepared the tables for various alpha by beta ratios, late and for total dose. For here example, I will tell you. So for 2 gray and 60 gray dose, that's a 200 centigrade and 60. How much equivalent if I go down to 700 gray? 700 centigrade or 7 gray per fraction I want to give, my total dose should be 2667 to get the same effect, or 800 into 3 fraction will give the same radiobiological effectiveness as of the conventional. So you can prepare the table by appropriately making choices of alpha by beta. And now I will come further, equations also will be there. Dale in 1986 gave BED equation for 2 fractions per day, 3 fractions per day, 4 fractions per day, and they are available. And in this equation, one more biological product, repair constant is there, and the value of repair constant must be known. We have calculated, we have estimated, published in literature, they are available, and you can see it here. For tumor, the mu repopulation constant is 0.69 per hour, for rectal reaction 0.46, available. They are available, and they can be used, or you can find out in your institution, your clinic, the appropriate values of this thing. Now, LQ model, because we just talked radiobiology, just I will take 3 or 4 minutes to wind up these things. That LQ model we have seen repopulation during the treatment triggering, and Travis and Tucker in 1987 added the constant to take care of repopulation during the prolonged overall treatment. If the treatment is 4 weeks, 5 weeks, 6 weeks going on, tumor also will start the repopulation. We have to take care of that repopulation. And they have given this equation, BED is equal to ND 1 plus D. This is my BED without the repopulation. And the repopulation constant gamma over beta T minus TK. T is the treatment, total overall treatment time. TK is called as a kickoff time. After how much days actually the repopulation of the tumor is triggered. Generally, for fast growing tumors, it is 3 to 4 weeks, it's 21 to 28 days. Moderately dividing, moderately growing tumor, it is 4 to 5 weeks. And for very slow growing tumor, like the prostate cancer, is of the order of 7 to 8 weeks. Now question comes, because of the COVID, how long we can prolong or how long gap we can give for a patient. If it's a breast cancer, even 5 weeks we can give gap, because repopulation may not start within that period. Prostate cancer, it can be even 7. But if it is a cancer cervix or head and neck cancer, which are fastly growing, 3 to 4 weeks is the time which you can delay your treatment. Otherwise, the repopulation will be triggered. Now, is this BED or LQ model can be applied to high-energy radiation like carbon therapy or proton therapy or the ion therapy? Yes. For low-energy radiation, my BED is equal to number of fraction, dose per fraction. Here 1 plus D. Here in place of 1, I'm going to take RBE of that particular radiation, which is maximum, and I will calculate BD. One example already we have calculated for the photon with 2 gray. Our late is 108 and our tumor is 72. If I use a carbon particles and I assume that RBE is 3 in Bragg peak region, then 4 gray per fraction, 6 fraction of the carbon therapy, the physical dose will be 24 gray only. Now this 24 gray in 4 gray per fraction, 6 fraction will end up into 81.6 gray of BED, because this RBE is, I have taken 3. And for late reaction, if I take it, it is 110. So you can compare the late reaction you are going to expect by the photon radiation of 2 gray, 30 fraction, 60 gray is 108, it's 110, it's comparable, but the tumor control probability is higher than the photon therapy. At the same time, you can see it's a Bragg peak. Particle therapy is radiobiology is totally different from the photon therapy. In the non-Bragg peak area, RBE is much lesser than 1. And if I take 1, the late effect in the outside the Bragg peak in the normal tissue is just 21. So very less tumor, the normal tissue morbidity outside of the tumor you can, and then you can escalate the dose that you can do. The gamma by alpha, that is the repopulation constant, you can derive. We have published a paper on this thing by using this isoeffective dose, plotting a graph, you can get gamma or alpha. And for the slow growing tumor, the repopulation constant is of the order of 0.3 or 0.4 gray per day, unit is gray per day. But for fast growing tumor, it can be 0.6 or 0.7 also.
Sorry,
Now,
Prof. Arun.
yeah,
Sorry, Prof. Arun, for interruption. Due to the interest of time, I think some participants requested that we can.
2 or 3 minutes. I'm coming down. Just
okay, thank you.
Advances in image guidance and all those things, hypofractionation. Now, is hypofractionation LQ model is applied or it is valid? You can see alpha by beta ratio is 10. Extreme hypofractionation, I will not be able to achieve better tumor control probability. But alpha by beta ratio is within 3, 4, 5. If I do the hypofractionation, my tumor control probability will remain the same. So for hypofractionation, even I just 2 slides will be there. For the same BED, different dose per fractionation, tumor control probability 1 fraction, 3 to 8 fraction of 10 gray, you can see is that the alpha by beta or LQ model gives the same result for even hypofractionation. For tumor radiobiology, SRS, SBRT, no need of any extra radiobiology, and they have concluded that do not support the need to change the LQ model. LQ model can be applied to even extreme hypofractionation. Comparison of 3 radiobiological models have been compared, and they have shown that the present LQ model, tumor control, local control probability, SBRT and SRS, it gives a very good result. Brenner has published a paper, a linear quadratic model is an approximate methodology for determining the isotopic dose, this thing, and he has shown that even up to 18 gray per fraction, LQ model holds good within little uncertainty. There are different kind of models. I will not go into that, Lyman-Kuchar and the Poisson method. And now we have got what we call as the biological optimization, biological planning. It is not the image guided radiotherapy, but the biologically guided radiotherapy. And we have treatment planning system by Philips, Varian, Eclipse. They have different kind of radiobiological model to take into the biological optimization. Biology is a very, very complex process, interdependent and these things, and therefore there are various challenges we have to take into account if we want to make. But In conclusion, according to our modern knowledge of radiobiology, LQ provides a best approximation to the cumulative effect of the range of biological processes, which in turn depends on the environmental and exposure conditions, and ultimate test of the validity of biological model is a clinical observation conclusion. Thank you very much for your patience hearing. Sorry for exceeding because I tried to bring down the slides, but the topic is so vast. So thank you very much. I will be able to take some questions if you pose to me.
Thank you so much, Professor Arun. I'm sorry to stop you, but due to the time interest, there are some questions from the audience. The first one is for Nazmu Mahadi. So he or she says thank you to you, and he or she wants to know some ideas about whole lung irradiation with low dose radiation for the treatment of acute COVID-19 pneumonia patients.
Okay, now here low dose radiation was being used in 1920s and 30s when antibiotics were not there to anti-inflammatory agent, as an anti-inflammatory agent to causing the inflammation and pneumonia and oxygen supply dropping down. Low level radiation works as an anti-inflammatory, cascading the effect it happens, and the needing of the ventilator and the criticality goes down, and it is being retried again, and clinical trials have started. This low dose of 0.5 gray to about 1 gray is not going to kill the virus. It just works as an anti-inflammatory if it given to the chest where oxygen supply has dropped down. A lot of papers have come up, clinical trials have started.
Thank you so much for the update. Yes, the ventilator will be one challenge for radiotherapy patients. Okay, the next question is from Ek Hao Ng from Malaysia. He's asking about fast forward trial claims that hypofractionation, for example, 20 gray per 5 session, is non-inferior to conventional treatment, for example, 40 gray per 15 sections. Can you please comment in terms of acute and late effect of this hypofraction treatment for breast cancer patients?
Yeah, as I told that the breast is a moderately growing tumor where alpha beta is of the 5, and there we do not go to extreme hypofractionation, but moderate hypofractionation, maybe 4.5 or 5 gray per fractions, and we treat them, we get a better tumor control probability with a manageable normal tissue composition because of the moderate alpha by beta.
Okay.
And that's being done.
Okay, thank you very much. So moderate fractionation is the answer, is that right?
See, only tumors which have low alpha by beta,
okay,
fractionation works. But
okay,
if alpha beta is large and it is comparable near to the alpha beta of the reaction normal tissue or late whatever reaction, then the hypofractionation doesn't work.
okay. Thank you very much for the information. There's another question from Dinesh Saroj. He's asking how to know kick-off time.
Okay.
I'm not sure. Yeah. I'm not sure about the questions, but the questions sound like this. How to know kick-off time?
Kick-off time is this, that when you are giving, this is a response of any assault. It is a natural response that if somebody is assaulting, we prepare ourselves. So here cell killing is happening, and therefore the message goes that we have to multiply, we have to divide to survive, and that triggering takes place. And it in the labs and also in clinical trial, it has been found that the repopulation kickoff starts in a fast-growing tumor in 3 to 4 weeks. And you can do these things, clinical trials, that your treatment time, prolonging the treatment time. A treatment time is 3 weeks, 4 weeks, 5 weeks, or 6 weeks, and you can see how the response is coming, and thereby you can see the factor of repopulation. But it is generally done into the laboratory lab, this thing to find out the triggering time.
Okay, thank you very much, Professor Arun. I think there's no other more critical questions. Let me see. Okay, sorry. There's one more question coming up. Hot questions. Okay, why there is a disparity in schedule between colleagues, though we have a protocol on fractionation?
See, as I told you that radiotherapy is an art. Radiotherapy, you take into account radiobiology and things, and then the perception that what tumor control probability I need and how much I can compromise with a normal tissue composition, how much I can manage. It is a clinical judgment, clinical choice. ETV and the confirmative index is good, you can plan, depends upon the fractionation schedules and the escalation of the dose you are going to do. So this is a confidence or clinical judgment of the clinician. So even in the same institution, for the same kind of thing, people try different kind of fractionation schedules and they achieve. That's
Okay.
a
Yes, thank you so much. Medicine is an art as well. Okay, we don't have much more burning questions for now. I saw some comments, there are a lot of comments saying thank you to Professor Arun for the very interesting and very well explained lectures.
Thank you.
Okay, I just got another question. Can you take one more, Prof?
Yeah. No, absolutely. Any number of questions. No
okay, this is for Gagan Preet Singh. He
Okay.
asked about, can you please comment on USC, LQL versus LQ model?
Okay. So as just I told, 3 models, it has been compared in one of the paper, this modified LQ model, the linear LQ model, and they found that for the hypo or the normal conventional fractionation, all the 3 model, they give the similar result. But there is another model that is called as equivalent uniform dose model, EUD model, generalized EUD model. There are a number, Lyman, Kuchar and Berman model, they are there, Poisson models are there. So, but they become more complex and more terms are involved into this thing. But some of the treatment planning systems are using this Poisson or the Lyman, Kuchar, Berman model, and depending upon the TCP, tumor control probability, and NTCP they are doing, assuming that the uniform, equal uniform dose gives the equal radiobiological damage. With this assumption, they go ahead. But many a times we have to see that effect, what we are assuming is a linear, it's a linear, that's a serial effect or a parallel effect. And will this low and high dose fractionation will have the same impact? Some assumption we do and we go ahead. So again, clinically correlation we have to do.
Okay, thank you so much, Prof. Arun. We do have more questions from the audience. Can I just open one more last chance to anyone who has questions or comments? You can just unmute yourself and try to talk. Anyone? Last chance.
Thank you, Prof. It was very nice, interesting, and very informative. We have gained a lot of knowledge from you. Thank you. It is updated and recent points were included. Thank you very much.
Thank you. Thank you.
Thank you very much, Prof. Karim.
Yeah,
Prof. Karim is a radiologist.
Okay,
Many years of experience in radiology. Yes.
Because I had to cut down many of the slides because many aspects they have got ready. It's a very, very complex and a lot of publication, a lot of papers are there, different aspects, different models they are there. But with the time, these things, I cannot put all the models and the conclusions into one talk.
Yeah, it's not
Yes,
easy.
we could understand. Yeah, time factor, time constraint. Thank you. Yeah.
Thank you very much. Okay, I think we do have more questions, or is it someone's talking? Let me check. Okay, anyone has any more questions for Professor Arun? Okay, if not, then I thank Professor Arun Chogoli again for the very informative and really well explained lectures, very insightful. For the participants, thank you so much for your attention. And for those who have not registered or encountered any problem to register for the CPD points, please kindly just drop us an email. You can send to Rajni, or you can send to Jin, or you can even email to myself, mentioning about you have problem to register for the CPT points. We will assist and we will issue the e-certificate in about 1 or 2 days time. So yeah, it's about 20 minutes past 4 p.m. in Malaysia, and in India should be about 2 o'clock now.
Yeah, 10 minutes. 10 minutes.
Okay. Okay.
I will take it over here. Okay?
Yeah, Jean, thank you so much. Thank you.
Thank you for the moderator. Thank you very much for Dr. Adam for excellent talk. So now I will have some more information for the audience. So the next webinar will be on August the 6th. So next month, the speaker will be Dr. Samyong Park from Singapore. His topic will be comprehensive photon therapy machine quality assurance and the guide ABPM PG224. So this is hope to see you there next month, and also the information about some more information about the continued professional development, the CPD points of these webinars. Actually, this was CPD points was endorsed by the Australian College of Physical Scientists and Engineering in Medicine. So we were 2 ways. You can register through the link here shown in these slides. The link I also want to paste once again on the chat, and also we will see the information in our background. So see if you are how you participate in these webinars. So, and I will paste the one again about this information, and then I need to stop it once. So someone who you need the CPD points, please register. Click the link and register your information, and we will send out the certificate like a I think within 1 week, probably. Okay. So that's all for today's webinar. Thank you. Thank you for the talk. Thank you for the moderation. Thank you all for the participants for joining up this webinar. So hope to see you next time. Bye-bye.
Thank you very much, Jean. Thank you very much, everyone. Take care and all the best. Thank you. Bye.
Thank you. Bye.